Welcome. In this lecture, we're going to talk about circular motion and centripetal force. We're really revisiting circular motion from a previous chapter, and we're going to look at it from the lens of forces. And for this one, we're only going to talk about things moving in a horizontal circle. We're going to get to vertical circles later on. So here we've got something that's moving in a horizontal circle. You can consider it like a tether ball, basically. And he's going around and around in a circle with velocity v. And as we talked about in a previous chapter, his velocity is changing all the time. So since the ball's velocity is changing all the time, that means that he has an acceleration. And the acceleration is going straight in towards the center of the circle of rotation. And an equation that we had for this centripetal acceleration right here is the centripetal acceleration is equal to the tangential velocity of the ball squared divided by the radius. So that acceleration A is v squared over r, and it points in towards the center of the circle, at the center of the circle. Now, if there's an acceleration, that means that there also must be a force. And we call the force that makes things move in a circle the centripetal force, just like we call the acceleration of things moving in a circle the centripetal acceleration. So if we look over here at the ball right here, the free body diagram, the only forces acting on the ball are the red forces here, and that's tension and mg, the weight going down. So the question that we ask ourselves when we look at things going in a circle is, what force or forces are supplying the centripetal force to make this object go in a circle? So the centripetal force is not a separate force or a different force. The centripetal force is actually applied by one of the forces already acting on the object. So in this case, what we see is the centripetal force, the blue F net arrow, is being supplied by the X component of the tensional force in the rope. So if we found the component of that force pointing in the X direction, which in this case is towards the center of the circle, then we're also going to see that that is going to be related to this angle theta. So if we took tension times the sine of theta, then that's going to give our centripetal force. And our centripetal force is going to equal our mass times centripetal acceleration. And here, t sine theta is equal to mv squared over r. So if we know the radius of the circle, and we know the velocity of the object moving in a circle, and we know the mass, then we can solve for the tension in the string. And I think if you'll notice, the bigger theta gets, the greater the tension in the string has to be, because the greater the centripetal force is going to have to be. All right? So the question we need to ask ourselves when we're doing these problems is, what force or forces are supplying the centripetal force to make this object go in a circle? And that's where we're going to start all of our problems. All right? So that our F net is going to equal the centripetal force, which is going to equal mv squared over r. This needs to be our starting point for these types of problems. So here's another classic example of a circular motion problem, something going in a horizontal circle. We've got a car going around a curve, and that curve has an effective radius of 45.7 meters, and the car is going around with some velocity v. So drawing the free body diagram, and this is a little bit differently than we draw our free body diagrams, but we're drawing the free body diagram for the forces acting in this car. We've obviously got the weight going down, and we've got the normal force pushing the car back up. But neither one of those forces are pointed anywhere near towards the center of the circle. That's the key for deciding which force is responsible for the centripetal force in these problems. It always has to be pointing in towards the center of the circle, because that's the direction of the centripetal acceleration. So if we look at the force of static friction between the tires and the road, that's what is supplying our centripetal force. We know that, one, because it's pointing in towards the center of the circle. Why? Because without the force of static friction between the tires and the road, this car would just shoot off tangent to the circle. It would follow its velocity at this instant right here, the tangential velocity at that instant. So remember that static friction opposes the direction of motion or desired motion of the object. So it's pointing in towards the center of the circle, supplying our centripetal force. So all sorts of different questions that we can ask based on this situation. If our curve has a radius of curvature of 45.7 meters, we can talk about how fast the car can go through the curve without slipping. We can talk about what is the maximum force of static friction between the tires in the road if the car wants to go through the curve at 25 meters per second. All right, all sorts of fun stuff. If we don't know what the radius of the curve is, we can say, well, the coefficient of static friction is 0.8. The car wants to go through this curve at 50 meters per second. What is the maximum radius of curvature, the minimum radius of curvature that the car can go through? So let's do an example problem with these numbers, and let's first talk about the maximum coefficient of static friction for the car to go through at a certain speed. So looking down from above, we've got this situation here. The radius of curvature of our curve is 45.7. And the car wants to go around at a velocity of, let's say, 20 meters per second. If we look at the car head on, this is a view from the side, then this is the the free body diagram. We have mg going down, we have the normal force going up, and we have the force of static friction going in towards the center. So with our starting point right here, we say that wow, that was interesting. We say that the centripetal force, F sub c, is being supplied by the force of static friction. We know that the centripetal force is just mass times the centripetal acceleration. We know that the force of static friction is the coefficient of static friction times the normal force. Sorry, let's remind ourselves what we're solving for here. We want the coefficient of static friction necessary for the minimum coefficient of static friction necessary for the car to negotiate this curve without skidding. So we're solving for mu. And let's see here. We've got this setup. So breaking this down even further, we know that centripetal acceleration is v squared over r. That's equal to the coefficient times the normal force. And looking in the y direction here, we've got the normal force and we've got mg. These have to be equal and opposite because there's no acceleration in the vertical. So that means the normal force is just mg. And conveniently, the masses cancel out because we didn't give a mass. So masses go away. And we're going to solve for the coefficient of static friction by dividing both sides by g. So we get v squared over gr is equal to the coefficient of static friction. Plugging in numbers here, we've got 20 squared over 9.8 times 45.7. That's equal to mu. Plugging that into the calculator, we end up with 0.89 for our minimum coefficient of static friction for this car to be able to go that fast through the curve. And when we recognize that 20 meters per second is more than 40 miles an hour, then we understand why this coefficient of friction needs to be so large. Normally the coefficient of static friction between rubber and asphalt is given as 0.8, so this car is not going to make it. He's not going to negotiate this curve without skidding. Now another question we could ask is, hey, let's say it's a snowy day, we have this same curve and the snow on the road has reduced our coefficient of static friction to 0.2. What is the maximum speed that this car can go through the curve safely without skidding? And we really just need to go back to an equation that we had already derived for this situation, this guy right here, but instead of solving for mu, we're going to solve for v squared. So if the coefficient of static friction now is 0.2 because of the snow, we are going to solve v squared over gr for v. So we've got v squared is equal to mu g r, and we're going to take the square root. So the velocity is the square root of mu gr. And plugging in our numbers here, we've got the square root of 0.2 times 9.8 times 45.7. And plugging that in the calculator, we get a maximum speed of 9.46 meters per second. 9.46 meters per second is how fast this car can go through the curve on the snowy day. So we see a much reduced speed. We're looking at around 20 miles per hour rather than close to 40 miles per hour if the conditions are dry. So those are problems moving in a circle. I'm going to give you a problem to work on for homework right now. So you're going to turn this in tomorrow as proof that you watched the video. All right, so for your homework tonight, let's go ahead and put some numbers in here on this initial example problem. Let's say you've got a mass of 0.3 kilograms that's hanging on this string. It makes an angle of 35 degrees with the vertical, and we have it making a circle of, oh, I don't know, let's say the radius is 1.2 meters. Find for me the centripetal force acting on the mass. Find for me its tangential velocity. And find for me the tension in the string. Whoops. Just the tension in the string. We'll talk about your answers tomorrow in class. See ya.